All right, this week we're going into one of the most exciting topics in learning analytics, which is to predict things. As usual, I will focus on the rapid minor parts in this video tutorial because some of the slides in the PowerPoint has already been supplemented by the videos we provided on Canvas, and I strongly encourage you to watch them as you go through the PowerPoints. All right, but I also picked some topics that I feel like that need more clarification. So the first one is supervised versus unsupervised machine learning. Um, so how do you tell if something is supervised or unsupervised model? The most straightforward way is to see whether it has a label. If you have a label in the data set, and whether your job is actually to teach the machine learning model to know what label to assign to your data sets. And by label, I'm not saying that it's only limited to those qualitative codings, for emotion, it can be happy, sad, angry, those kind of labels. It can be beyond that. It can also be something like a bounding box, like here. So that would just be a coordinates about uh the left, the top left corner, and also the right bottom corner, so that you can just draw a box um on the picture, and then you also assign what this box actually capture. For example, here we have the handsome George Clooney. So the label is not just the typical label we think of. It's more like an annotation in any form. Like the bounding box could be also be the label. So as long as you see some labels in your data set, and your job for the machine learning is to learn how to assign these labels to your data sets, then you're doing supervised learning. Otherwise, it is unsupervised. And a typical example of unsupervised learning is clustering. And for example, you have 500 students with their behavioral logs on the MOOC, and then you're trying to get 4 different student learning profiles from this log data. And one typical way to do that is to use clustering, which we'll cover in the later week. All right, so that's it for supervised and supervised learning. And so now we have come to cross-validation on slide 12, which is an important technique in machine learning. Remember in our last tutorial, I mentioned PCA has the potential of avoiding overfitting by reducing the number of features in the datasets. It turns out that cross-validation is a way better choice to avoid overfitting. Hopefully you still remember what overfitting means. To recap, overfitting suggests that your model performs really well with the training dataset, the dataset that it has seen and learned from, but performs very poorly from the testing datasets. Cross-validation is used to see how well can our model perform with unseen datasets. In these slides, we are dealing with the most commonly used techniques for cross-validation, k-fold cross-validation. Do note that there are other cross-validation techniques, such as leave one out, but let's stick with the common one. So how does k-fold cross-validation work? First, let's say we have 100 entries or rows in our data sets, poor we, a very small data set. And let's say we are doing tenfold cross-validation, tenfold, okay? So we will first split our data into 10 equal-sized subsamples. Why 10? Because it is tenfold. If we're doing fivefold, then it will be split into 5 subsamples. Second, we will have a sliding window that is 1/10 long, and the data in the window will serve as the testing data. The rest of the 9 subsamples will be used as training data. We will have some evaluation metric, such as prediction accuracy, calculated from the testing sets. Then we will slide the window to the next subsample and use the subsample for testing. The others will be training datasets. And repeat the evaluation. We slide the window 10 times until we have used every subsample for testing. And finally, we will have 10 evaluation metrics collected. For example, 10 accuracies. We will then average these 10 accuracies to understand how well our model performs. So how our final accuracy will be to suggest no overfitting is found? Pause here and answer to yourself. All right, you get it. The average evaluation metric from the tenfold cross-validation should still suggest a good performance. Otherwise, we might have an overfitting issue. Alrighty, now let's do some rapid mining. So we've come to slide 14, the exercise for linear regression. And in this exercise, we will construct a linear regression model. And then we will also try to determine how well this model performed and examine how significant each attribute is in the prediction model. All right. So slide 16 gives you what your final workflow should look like, or what they call the process in RapidMiner, how your process should look like. And let's get started. And let me move this away. Okay. So on slide 17, it said that we should import the data. Click import data, and then my computer, and then the old good learning analytics course folder, and module 3 datasets. Remember, you need to download this dataset from the Canvas page in module 3. In the PowerPoint, it says dataset.csv, but we have renamed it to be clearer. So it's module 3 datasets, all right? And click next, next, next. Where do I want to store it? Local repository and data. I just click here. You can save it anywhere, wherever you want, and you can create a new folder if you want. So I'm just gonna save it under the data. Okay, it's imported, and now let's go to slide 18. So it said we should go back to the design because we need to go drag some operators. So those boxes you see in the PowerPoints, they are called operators. The first thing we need to drag in is actually the data set itself. So where's my data sets? Module 3 data sets. All right, drag it, and then you should see that it's already importing the data for me. So this is a retrieve data operator, and you can see that it has already filled in the path to the data for me, and it should just read the data for me. All right, and let's go to slide 19. First, we need to get this select attributes operator. So one thing to remember is that never try to remember where the operator is located at. Try to use the search bar, the search box here, to search for the operator you're trying to find. All right, and select attributes, click it, and we should connect it out with EXA, which is example. So that's how the RapidMiner call data with its example. All right, so example just means data. And let's see, we need to click select attributes, and then attribute filter type, change it to subsets because we're trying to filter something. And then click select attributes and find grade score. Double click it. You see it should be moved from the left to the right. And then the next one is message discussion. And finally, time material. Okay, now we have select all the attributes and click apply. Oh, so wait a second. What we have just done, right? You told me to drag this operator, but what it does. So as you can see, this is actually for filtering or just keep a subset of the data. And that's why we chose the subset option here. And the select attributes, they're all columns, they're all features, right? So what we mean is that we only want to keep these three features in the filter data sets. So we don't care about any of this for now. And then we just want to keep these three. That's what we just have done. And now let's go to slide 20. And we should use set row operator, drag it, and connect the example with example, and click set row. For the attribute name, we want to select grade score, and for the target row, we want to set it as label. And also we want to click the edit list button, and for the time material, we want to set it as regular, and for the message discussion, also regular, and hit apply. So what is it? What is this? It's just some annotation that we are giving the machine learning model. So when we set the grade score to target row label, it means that this is going to be our dependent variable. And when we add these two other features, these two other columns as regular, it just means they're going to be our x. So actually, the edit list part is actually redundant. Even though you're not doing the edit list and set them as regular, the default is that every feature is just regular. All right. The important part is that we set the grade score as label so that we have a dependent variable. Make sense? All right. Let's go to 21. It's actually explaining the cross validation, which I have done, and go to slide 22. Okay, so we need to add the cross-validation block operator now, and right-click on the white space, and then insert building block. Choose numerical cross-validation because we're doing regression, all right? So it's not nominal, it's not category data, it's actually continuous data, numeric data. So choose the numerical cross-validation operator and put it here. So we align them. Okay, slide 23. We should first connect the set row with the with the validation operator, and then we can single click on the validation operator to see what kind of parameters we have here. So it says number false 10. Okay, I can live with that. And now let's double click on the validation operator. Double click, right? So on the left hand side, we have the training phase. You see we have the training data input for the generalized linear model, and then the model outputs, like which is trained, be applied to the applied model operator, which just means that predict something for me. And then we also have the testing data sets. You see, if you hover over it, it will tell you it's validation.test set connected with the unlabeled. So the UNL just means unlabeled data. That's because we are trying to predict something. We can't have any label, right? Or else what are we predicting? And then we pass the results, the prediction to the performance to evaluate. And that the right hand side is just the testing phase, the testing process. And let's go to slide 24. It turns out that we are not going to use generalized linear model. Instead we're just going to use a simpler one, which is linear regression. And we just need to connect the training with training, model with model, and we are connected. And then let's go to slide 26. We can click on the linear regression. You see, if I click on it, I will have the parameters show up on the right hand side. So if it's too small for you, like it is like this way, just try to make it bigger. All right. And then I think I've already showed the advanced parameters by default. So what you will see is probably like this. You don't see that many parameters as I do. So just click the show advanced parameters here. to show the full set of things that you can configure for the linear regression model. And what we are going to do is that we change the M5 prime to none, because the M5 prime will drop the betas that are not significant. So if we choose none, we will have all the betas shown for all the coefficients for every independent variable, um, whether they are significant or not. All right, and let's change it to none for now. And let's go back. I think yes, we should go back. On slide 28, yes. So we need to click go back. Just click the process or the arrow button to go back, and then one last step to connect all these outputs so that we can actually see them. All right. So this seems good. And in slide 28, we are ready to hit the run process button. And let's see. Okay, now you should see that we are automatically jumped to this results panel, and we have several tabs. And the default tab is the performance vector, or just performance. So for regression model, we usually have, I guess, well, it doesn't have the R squared here, but the squared error is also a metric to help us compare with models. So we want smaller errors, right? Because for example, if you're doing a linear regression model and also a generalized linear model, and also maybe a decision tree regressor, you will have different root mean squared error, and then you might want to choose the one with the smaller RMS RMSE. And remember, I told you that the cross-validation will average the evaluation metric. So I'm not lying. That's why you can see the squared root mean squared error is actually 5.833 plus or minus 0.560. So that's because there's a range in this tenfold cross-validation. All right. And the squared error, the root mean squared error is just the average of the squared error and also do the square root of it. Um, and they're basically the same thing. And linear regression. This is so we were in the performance tab, and let's now click on the linear regression tab. And this is the thing that we can see all the stats. I guess the stats results, testing results. We will see that um, these two independent variables, they are all significant predictors to the dependent, which is the score. So which is good, and it just tells you the I guess the thing you're familiar with if you have ever done linear regression, tells you the coefficient value, what's the standardized coefficient, and what's the t statistics, and also what's the p-value associated with the t. Yeah, and that's it. And that can you can use this table to help you interpret whether some variables are useful to be a predictors or not. All right, so now let's go to slide 39, which we will build a decision tree classifier. It's a classifier because we are not predicting a continuous score of the grades, but we are doing the grade letter, which is category, right? So this is called a classification. We are predicting some categorical variables. And the complete process will look like this. It's very similar to what we just have. We will retrieve the data, select attributes, just keep the columns we care about, and also set row, what's our independent variable and what's our dependent variable, and also set up the validation operator. All right, now let's go to slide 40. Okay, and let me move this away. I will just delete this validation operator because that's for regression. And in slide 40, it tells us to click select attributes operator. And then we need to change from grade score to grade letter. And the other two independent variables are the same, but we just change the dependent variable from a numeric one to a categorical one. And hit apply. And slide 41, we need to set the role of the grade letter to label. And then slide 42, we need to, hold on a second. In slide 41, we need to create the validation operator, which is a nominal this time. And connect the example and also double click it. Okay, so by default, we're already using a decision tree here, and it's already connected for us. So if we click on decision tree, there are several parameters we can tune. So if you, for example, if you increase the maximal depth, it's likely that the model will perform better in the training, especially in the training data sets, but also increases the risk of overfitting. And we can just use the default set for now. Let's just use the default. And in slide 43, okay, we need to go back first and then connect model outputs and run the process. All right, now we've come to the performance of the decision tree. And this table you see is what we call a confusion matrix because it is quite confusing. All right, so how many true C we have? True C means that the letter grade C, the number of letter grade C in the data set. So we have this column, which is 32 plus 19 plus 0, and that is 51, I mean. And then how many did the model predict as letter C? And that is 32 plus 23 plus 2, which is 57, right? And the recall, what is a recall? So recall is by class, or by class I mean like by category, like category C, letter B, and letter A. So the recall for class C is 32 divided by 32 plus 19 plus 0, which is 62.75%, right? That's how you get this number. And it just means that among all the true C, how many were correctly predicted? And that's what the recall mean. And so we also have something called precision. So a precision is something, so how do we get this number? It's just 32, it's just this row basically. We get 32 of them actually correctly, and we actually predict 57 as C. The model predicted 57 cases as C. So the precision of it is actually 56.114%. You see, right? So the precision just means that for all the predictions we make for a certain class, like for example, for class C, for grade letter C, for all the prediction we make for this case, how many of them are actually correctly predicted? So that's just 32 divided by the whole thing here, and that's how you get the precision. All right, and we also have the accuracy here. The accuracy is just like the number of correctly predicted number over all of the cases. For example, if we have 300 in total, I think it's 300. If you see 300 examples in total, and how many of them are actually predicted correctly. So it's 32 plus, you see for B is 167 plus 5 over 300. And you see that's how we get the accuracy of 68. All right. And the kappa, if you have ever done some qualitative research before, then you might be familiar with it. This is just the Cohen's kappa. for inter-rater reliability. So we want higher kappa in this case. The maximum should be 1, and we want something that's closer to 1. And right now, this is just miserable. And that's also suggests something that accuracy is not a very good evaluation metric that you might want to use for classification, because you can have some fairly decent or even really good accuracy, but your kappa can be very, very low. Okay, imagine the case that we're doing a tumor diagnosis machine learning model. So we want the model to tell us whether a patient will have cancer or not. And we know that the possibility of having cancer is really, really low. For example, it might be 1%. So only 1% of people will have cancer. So to achieve a really super high accuracy, what we can just do is that we let the model to always say no in this case, because we know that most people will not have cancer, and we can have a pretty decent accuracy, and that is almost 100% accuracy. But is it a good model? Probably no, because it loses the value of the machine learning model, right? Because we actually want the machine learning model to tell us whether a person will have cancer or not. If all it does is to say no, then what's the point of having it? And by the way, you might notice that the accuracy or the evaluation metric you get is actually different from mine or from the PowerPoints. That's totally normal because there's always some randomness in machine learning. If we run the model in a different environments, we can get different results. And but the results shouldn't be, very big. The difference shouldn't be very big. In the PowerPoints, it was something like 68.33. Here is like 68%. So it's very close. And now let's go to see the tree structure. And one of the reasons why people like decision tree is that it's so easy to interpret. It is just like the if-else diagram you can have. And for example, for time material, if it is greater than 43.35, then we will enter this node, or else we will just give the gray letter C here. So it's really very straightforward to interpret, and it can help offer some implications for teaching and learning. The problem is that it tends to overfit, and that's why in the PowerPoint we also talk about random forest, which I will discuss very soon. But before that, let's see something that you might be confused with. So in the validation operator, when we click the decision tree, we see all these fancy parameters, and you probably don't understand what they do. So, and they all affect how the model will perform. So, since these things are important, is there a way that we can do so that we can, automatically choose the best value or combination of these parameters for us? Actually, yes. So let's go back to our process. And let's remove the validation operator. Instead, what we are going to add is called optimize parameters grid operator. So what this does, I'll explain later. Just let's follow me and set up the process for now. So we still need to connect the example with the inputs and then connect the performance. And I think that's it. We just need to connect the performance of it, or actually the model, and just connect everything. Okay, and within it, let's still add the nominal cross-validation block here. And let's click input, connect input with example, and model with model, and performance with performance. Okay, and double click to enter the validation operator. You'll see that we're still using the decision tree. Okay, and now let's go back to the root process. Just click the process here, and we're back. Click the optimize op parameter. So, and let's click the edit parameter settings. And click decision tree in the operators. Okay. And let's just add some just double click these parameters. Actually, you can't. You have to click the right button here to make it selected. And let's just try some of them. Okay, so I selected 3 parameters from the decision tree, maximal depth, and apply pruning, which is a boolean, and minimal gain. So here in the range, let's try, from 1 to 100 steps, and then true. And 0 to infinity, that's too many. From 2, I guess. All right, so you can just play with the number as you want, but let's talk about what we are actually doing, right? That's the more important parts. So we are adding this optimized parameter, or what they call grid search, a grid search operator here, to actually search for the best combination of parameters we can have. So first we select the decision tree, and then we select some parameters of the decision tree to make them selected. In this case, I select these 3 parameters, and then if I click one of them, I can set a range of values that I want the RapidMiner to try. For example, I type minimum 1 and max 100. The steps is 10. So it means that I will have 10 value created between 1 and 100, and they're created linearly. Like you can see the value I created is 1, 11, 21, 31, 41, actually 11, I think. Yeah, 11 values created. Um, and also for the apply pruning, because it's a Boolean, it's more fairly straightforward. You just have put the true and false here. And if you don't want to try, if you only want to try false, you can just move the true to the other side, and it will just be, just it would the RapidMiner will just try the false of applying pruning here. But I mean, what's the point of including this parameter if we only try one value, right? So we want to try both of them. Um, and then minimal gain, I set from 0 to 2 with steps of 10. So we just create a value linearly for me. And then you see that it will say how many combinations I have is 242. So it's basically 11 choose 1 times 1 choose 2 times 11 again, because we are doing that from 0 to 2, and with steps 10, we only have 11 values here. So basically, we have this many combinations to try. So as you can see, this is a very straightforward way to find the best parameters of a model, but it can also be very small. So for each combination, it will go through the validation process we set in it, and we have to go through the validation process 242 times. That can be really, really slow if your model is very fairly complex. So especially if you also have a very big data set. So that's one thing we can try. Let's see. Click the running, and you see it's not like immediately showing the value now or the results now. And we can see that uh, the best performing accuracy, wow, that's actually a very big boosted. So remember, originally we only have like 68 something accuracy. Now we have almost 90, and the kappa increased from zero point 0.3 to almost 0.8 now. So that's what you can do with the optimized parameter operator, and sometimes it can make a huge difference on your data on your results. Okay, now let's do random forest from slide 50. And this is what your process will be like. Actually, at the end, we also add a uh, weight operator here. It's not showing in the picture, but we will get there. Okay, so let's go to slide 51, and we just need to, okay, I just delete my nominal cross-validation operator, so I need to recreate it and enter the validation by double-clicking, and we want to replace the decision tree with random forest. Drag it, connect it. Okay, so that's pretty it for the random forest. No, that's not it. So one thing you need to know about random forest is that if you care about your performance, like how accurate your model can be, always go with the random forest, right? Because it use this fancy mechanism called ensemble. And that's one of my favorite words or jargons in machine learning because that's just really vivid, right? Because originally we have just one tree, the decision tree, and the random forest is made of like lots and lots of decision trees, and they're all working together to get a prediction results. And that's just like ensemble, in the music, people play together. So that's really, I guess, my favorite word. Anyway, so we can also add this importance of feature operator. Let's just type weight by tree importance and drag it here. So connect the model with the random forest, and then other things with the rest. You might when you click, like, say, for the example to the oh, actually no, example to the rest. uh, it might make you look like, it might make it look like that it's going through this weight by tree importance operator, but it's not. Okay, it's coming behind it. And let's just connect the test and also the performance. Okay, and if we run it, we will see that, wow, the accuracy is not bad, the kappa is not bad. And what's more important is that we can, oh, I forgot to connect one thing. Heads up, you need to connect the weights to the results so that we can actually see that. And let's do it. And you see that the attribute by attribute weights, the weight by tree performance tab, and it will tell you how important a independent variable is to predict a dependent variable. So you don't need to worry about the unit here. Like, you don't need to worry about what does 7.516 mean exactly. You just mean that we just know that the higher the weights, the more important the attribute or the feature or the column is. So this can, to some extent, help you explain your random forest model because unlike decision tree, um, we only have one tree structure. That's quite straightforward to interpret. But for the random forest, you tend to have 100 or even 200, 300 trees, and that's almost impossible for you to go through all of them and also make something meaningful from the tree structure. So using the attribute weights, the weight by tree importance operator, we can know, we can have some information on how important a attribute is to the prediction task. All right. So that's pretty it for the random forest. Okay, so for this week's homework, we're going to do the data analysis too, which is a group work. You can find your group information in the assignment page. Just like click here, and then you will also need to download this worksheet that you need to fill in your RapidMiner results, and it looks something like this. So we have three questions for you, one using linear regression and how you can interpret the results. There's an example for you already. And also doing a decision tree model, a random forest model. All right, so everything we've just covered. So it should be quite straightforward. But again, if you have any questions, feel free to come to the office hour or just schedule a Zoom meeting with me, and then I'll be glad to help. All right. Good luck with the homework. Bye.